so in principle, quantum mechanics explains all of chemistry, and other things as well, but chemistry is what I know something about. For example, how electrons stick to nuclei to form atoms, how atoms form bonds and molecules, what energies, colors, shapes atoms and molecules can have, how they move, how they react. So it's worth knowing something about. So Erwin meets Goldilocks, that's Erwin Schrödinger, and here's Goldilocks. And as Jack said, it's a practical primer of quantum mechanics. It's practical. We're not going to talk about philosophy and Schrödinger's cat and that sort of thing. I just want to show you how it works in chemical context. Or understanding the influence of negative kinetic energy. Okay, so on quantum mechanics, these are quotes from Nobel laureates. Schrödinger himself said, "I do not like it. I'm sorry I ever had anything to do with it." Max von Laue said, "If that turns out to be true, I'll quit physics." Niels Bohr, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." Feynman, I think I can safely say that nobody understands quantum mechanics. But here's some from non-Nobel laureates. If you want to understand quantum mechanics, just do the math. Now, there are two things about this quote. One is understand. Does ability to do the math constitute understanding, right? And in my case, I took a course in quantum mechanics and I did the problems, but I certainly didn't understand it after that. It was only when I started teaching it that I began to get an idea of what was involved, really. And just do the math. You may know this. That's the one formulation of the Schrödinger equation. You can buy this pillow for $23 on that. Okay. So that's what Dyson said. But I say more look at pictures of waves. So that's what we're going to talk about today is pictures of waves to understand quantum mechanics. So understanding these wave pictures requires reviewing two quantities. The first one is altitude, up and down, and you assign a number to it, positive for up and a bigger number for higher up, and so on. So altitude's pretty familiar. And curvature is less familiar. Now, actually, what's involved is not curvature. Technically, it's del squared, the Laplacian. But let's not worry about that. It's curvature. It's like when you drive a car, right? You turn the wheel, and the car then executes a curve. Right? Like if you turn to the left, and we'll call that positive, the car goes up as it's going along. Right? And if you turn it to the right further, it turns to the right and a sharper curve. Right? That's curvature for our purposes. Okay, so consider the topography of the Holy Land. So here's a profile of the topography of the Holy Land from Jaffa to Amman. And we'll take this wave as our example. Okay, notice that Jerusalem is 2,500 feet. Ezra knew what he said when he said, let them go up to Jerusalem, which is in Judah. Right? Now, actually, it's not that far up. The heights are shown out of proportion here. Those are miles, these are feet. Right? So there's a factor of 25 difference in the scale. What it really looks like is this. Okay, that's 25 times less. But still, if you go up to Jerusalem, you realize you're going up. If you're on a bicycle, it's nothing. Okay, now, but for our purposes, we're going to blow it up so you can see it in greater detail. Okay, so altitude is, of course, a familiar concept. Jerusalem's 2,500 feet, but it's not as high as Amman, which is 3,000 feet. And you'll also notice this little rise you go over before you get down to the Dead Sea. And poor Jaffa over there on the coast is only 115 feet. But it's not the lowest, because the River Jordan is minus 1,100 feet. All right, so you can have negative values of altitude as well as positive. Okay, so that's all familiar. Now let's just look at this as a curve. For altitude, we'll actually say amplitude. Because when people talk about waves, they talk about amplitude. They don't use the word altitude. So I'll use the word amplitude, but it's the same for our purposes as altitude. Okay, now the other concept is curvature. Now you can see curves here, of course. Suppose you were in a car starting off the left and you get to Jaffa there, and you have to turn right, curve to the right. Now we'll call that curvature there, when you do a right turn, we'll call that negative. And the reason to call it negative is you turn in a downward direction. right? Here's another place, right, where you turn to go down. Here, in fact, you end going up slightly across the coastal plain, but you turn toward going down, right? If you turn the other way, you'd go up even more. So we call, in this picture, turning right negative, and we'll give a number to it according to how much you have to turn the wheel. Okay, and there are other places where you have to turn to the right. But of course, there are places where you have to turn to the left as well, like down here. Okay, so you can have positive or negative curvature. Now we're going to talk about a more complicated thing, and if you get this, you've got the whole thing. This is the toughest concept in the whole thing. It's curvature divided by amplitude. Okay? Now, where is this particularly dramatic? Well, here you've got a very sharp curvature, right? So that's a pretty big curvature divided by amplitude. Because the amplitude isn't too high, so you don't cut it down very much and divide it by that, right? The ones up here are smaller curvature divided by amplitude because some of the curvatures aren't as big. This one's pretty big, but they're all much higher, so they get cut down more. So, but the most dramatic, one of the most dramatic ones is here, probably the most dramatic. It's a pretty sharp curve, right? But it's really low. Remember, Java's only 115 feet. So that turns out to be the biggest value of the curvature divided by the amplitude. Okay. Now, notice that all these are negative numbers. They're all right turns curving down, right? And the positive amplitude, they're above sea level. So the number that you get, curvature divided by amplitude, for all those is negative. Okay? Now, down here, you're turning up. So it's a positive curvature, but it's a negative amplitude. So again, it's negative. All these are negative in curvature divided by amplitude. Right? So all normal values of curvature by amplitude are negative, like a water wave. Right? When it's up, it's curving down. When it's down, it's curving up. Right? So generally, it's negative. Right? It's curving towards zero. Right? When you're down, you curve to get back to zero. When you're up, you curve to get back towards zero. That's normal. But not all of them are like that. Some values are positive of curvature divided by amplitude because they're curving away from zero. Now tell me when I get to a place that has that property. Curving away from zero. Here, right? Okay. Where else? There. Right? And here. Okay. So there are a few values where you curve away from zero, but most of them are curving towards zero like the normal water wave. Okay. So if you got this, you got it. Curvature divided amplitude. Right? Usually negative, sometimes positive. Okay. Now, an interesting property of this is that if you went to the original contour or that realistic one, they all have the same value of curvature divided by amplitude. Because when you go down to a lower amplitude, you also go to a lower curvature. You don't have to turn the wheel much to go along here. Right? Okay, so that's an interesting property wave. Now the Schrödinger equation, this is a more compact version that I showed you on the pillow. H psi equals E psi. It was formulated in January 1926. Not exactly in those terms, but that's the idea. Okay, now that thing is called a wave function. Now, what's a wave function? Okay, psi assigns numbers to the particle's position. So here are various numbers, and here are places the particle could be. Okay? So we have different positions, and psi says that if the particle's at this position, it's positive. If it's here, it's sharply positive, and so on. Okay, so that's a regular old graph. So psi is just a whole bunch of numbers, each associated with a different position of the particle. Okay, now, what do these numbers represent? I hear you ask. This was a really tough problem, what they represent. This is Werner Heisenberg's research group in Leipzig in 1931. So this is 5 years after quantum mechanics was invented. And he got the Nobel Prize for quantum mechanics in 1932. So all these colleagues of his students were really proud. They knew they were working on the real thing here, right? So here's Rudolf Peierls, who became a great nuclear physicist at Birmingham and then Oxford. Here's Victor Weisskopf, who became in quantum electrodynamics. He was the chairman of physics at MIT. And the guy behind Heisenberg there is Felix Bloch, who himself got the Nobel Prize for nuclear magnetic resonance in 1952. Now these guys are posing for a picture of the group, right? They know they're in a very key position, so they're all focused on the camera, right, and on posterity, except for Block. What's Block doing? He's looking at psi. What the heck is psi? Now, 5 years earlier, just at the time, just 6 months after Schrödinger formulated the equation, Bloch and his friend Hüppel, who was a student in Zurich at that time where Schrödinger was, composed this doggerel, which is Erben with his psi could do calculations, quite a few. We only wish that we could glean an inkling of what psi can mean, right? The meaning wasn't obvious to these guys. It was a tool. Psi is a tool for calculating the energy of particles. Psi itself wasn't anything except it was just something that allowed Schrödinger to calculate what energy, because it was so funny that you couldn't have any old energy for an atom. Only certain quantized values of the energy. It wasn't too surprising that atoms were particulate, right? That matter couldn't be infinitely subdivided, that you went down finally to an atom. But that energy wasn't continuous was really surprising. And that's what caused the revolution, really, around the turn of the century. Okay, so this was a tool. So first we'll enjoy using this tool, learning how to find particle energies from these waves, right? And at the end, we'll learn what it means. Okay, so here's the Schrödinger equation. Now, actually, it's many equations, because you remember psi has a value at all different positions. So this equation happens, different values, but always this is true wherever the particle happens to be. Okay. Now, unfortunately, this does not mean h times psi. Right? It's a sort of recipe that allows you to get a number, h psi, when it's applied to psi, right? So it's just sort of a formula you go through that will make a number over here. It's not multiplication. Fortunately, on the right, it is multiplication. It's e times psi. Okay, so we have h psi equals e times psi. Now, that we could divide by this one since that's multiplication. So h psi, that's a number, divided by psi, is e. Now, what's e? E is the energy of the particle, right? And this is a particle that's not interacting with anything else, so its energy is constant. So it's like this, like a spring. Okay? So this has no energy, this thing here now. If I move it a little bit, I'm bending the spring, that's giving it potential energy, but it's not moving, right? If I release it, right, it goes back and forth. When it's in the middle, it's going fastest. When it gets to the end, it slows down. So here in the middle, when it's doing this, in the middle it has a lot of kinetic energy, but at the extreme it has none. You're trading back and forth, but the total energy is the same all the time. Okay, so this is the same idea. This is the total energy of the particle is the same, but depending on the position of the particle, you trade off between potential and kinetic energy. Okay, so the total energy, constant, is equal to the kinetic plus the potential energy. Okay, so h psi over psi divided by psi is a formula that allows you to get the sum of the kinetic and potential energy. Now the potential energy part of this is nothing. It's given to you at the beginning of the problem. Like in this case, how far I bend the spring says how much energy is stored in it. Right? So you have a rule like that, or the attraction of positive and negative charges, something like that. Okay, so this part is given, has nothing to do with psi and how psi varies. It's just a certain energy. Okay, but this part, the kinetic energy, hold your breath. Now I suspect that a lot of you remember from old times what the formula for kinetic energy is in classical mechanics. Can somebody tell me? 1/2 mv squared. The mass times the square of the velocity is the kinetic energy. Right? 1/2 mv squared. Good. Okay, that's a fine approximation for our great-grandparents. Right? But they didn't know anything about tiny things like atoms and electrons and nuclei, and that was where people got into trouble when they started measuring things about these and found out it didn't work. Okay? So, it's not that. Now, what is it? Well, here are a couple of quotes. This is going to require a willing suspension of disbelief, because what I'm going to tell you is so outrageous that you think it can't possibly be true. But remember what Henry James said in Art of Fiction. We must grant the artist his subject, his idea, what the French call his donné. Our criticism applies only to what he makes of it. So just grant Schrödinger and me that we're going to calculate the kinetic energy and we'll see what comes of it. And it turns out that everything comes from it and it's right. Okay. So the kinetic energy, the formula for it, begins with 1 over the mass. Remember, normally kinetic energy is bigger for a bigger mass, other things being equal. But here, it's less for a bigger mass. That's crazy, right? And then it's multiplied by the curvature of psi divided by psi. That's this thing we talked about earlier. It can be curving towards 0, like that, or away from 0, like that, right? So those are positive things. So this curvature psi divided by psi is kinetic energy times 1 over the mass. And note that this involves the shape of psi. You're more accustomed to dealing with values of things rather than whether it's curved or not. So it's the shape, not just its value. And fortunately, it has a negative number with it. It's negative because, remember, curvature psi over psi is normally negative. So if you want to have a positive kinetic energy, you have to put the negative sign in. And this is not how Schrödinger thought up the Schrödinger equation. That's my analysis of it. Okay, so that's it. Now, what does it mean to solve a problem in quantum mechanics? You're given something, and you have to find something. What you're given is a particle, mass and potential energy. This formula of what the potential energy, how far you bend the spring. Right? Okay, so it's the mass of a particle and a formula that gives its potential energy at every position it could have. Okay, and you have to find psi, such that h psi over psi, remember that's the formula for the kinetic plus the potential energy, is the same everywhere. It's the same here, or at Dan Rosner, or in Orange, or in San Francisco. It's always the same value. Okay, because that's the total energy, and the particle's not interacting with anything else, taking on or giving off energy. And psi has to remain finite. It can't go to infinity. Okay, so first, it has to be the same everywhere. And second, we won't allow ones that go to infinity. Now, of those two, the one that looks challenging is this first one. Formulate a wave so that that works. But it turns out that that's not trouble at all. Because here's the, making E the same everywhere seems to be a tall order. Because remember, the potential energy is going to change at different positions for the particle. And the value of this wave is going to change, and its curvature is going to change. The changes in this have to balance changes in this, so that this is always the same. That sounds sort of tough to do. But in fact, it's easy, because you can just use the equation to do it. The shape of psi must be such that changes in the value and the curvature offset changes in the potential energy to keep their sum constant everywhere. Okay, so there it is. First, we're going to rearrange the Schrödinger equation to get a formula to trace out waves that will satisfy this equation. Now, here's how we're going to do it. First, you multiply both sides by -1. Okay, so everything's positive comes negative. Okay. Then we're going to, having that, we're going to add v to both sides. So it'll cancel out here and you put it in over here. Okay? And then we're going to multiply both sides by m and also by psi. So that will destroy it here and put it over here. So that's it. So this is just, again, the Schrödinger equation. Just simple algebra on it. Okay, but what is this? Curvature of psi equals psi times m times v minus e. So m and v, remember the mass of the particle and the potential energy at any given point are given to you at the beginning. You know, how far you bend this, what energy is involved. So if you can guess E, then you know everything on the right? Start out with a certain value of psi. And remember, you can use any one, because if we blow up the wave or shrink it, we always have the same curvature over the value. Okay, so start with a certain value. And this tells us then how to turn the steering wheel, what the curvature is. So all we have to do is start out and keep recalculating that and steer according to what Schrödinger's equation tells us. So it's on autopilot, right? Once we guess E. So adherence to Schrödinger equation is guaranteed. Now, but will psi remain finite everywhere? Because as long as it's normal, as long as you have positive kinetic energy, that means the wave is curving towards zero. So it's never going to go to infinity. It'll curve down before it goes to infinity. Or if it's down, it'll curve up and never go to infinity. No problem. But it curves away from zero when the potential energy is greater than the sum of the potential and the kinetic energy. That is, when the kinetic energy is negative, it's going to curve away from zero. And if you're a region where that's happened and you're down, you're going to be curving away, keep curving, zing, you're off to infinity. Or if you're up, you're going to zing off to infinity. Right? So that's the real problem. Is you can use the Schrödinger equation itself to make the curve, but you don't want it to go to infinity. Okay, so in regions of negative kinetic energy, you'll have this problem. Okay, so what we'll do is just guess E, turn on the autopilot, let Schrödinger steer, and see if psi blows up. That's what we'll do. Okay, so here's Schrödinger meets Goldilocks. And now I'll show you this, and I have to get to my keyboard to do this, so I'll kneel down. Okay, so we got a little program that does this. Well, here we have to, first in this program, we have to define the problem. That is, we have the mass and the potential energy. Right? That's given to us. So we'll choose the mass to be 1, that's the default. And we'll assume that the potential energy is the same everywhere. No strings to stretch or anything. Okay? And we'll create that. And I'll make the dimensions such that the energy goes up higher than that. Make it go to the 60s or something. And make this bigger. Okay. So here's the total energy right here. Or pardon me, this is the potential energy, and it's constant all the way across at 0, right? And here, about this value, 0 for the wave function, I'm going to let Schrödinger steer and trace out a curve and see if it goes to infinity. Okay, so what we have to do is guess an energy. Okay, so somebody guess an energy. Some small number. 0? Yeah. I couldn't hear. 10. Okay, we'll do 10. Bingo. So there's Schrödinger steered, and that's the wave that came out. And you can see it's a normal kind of wave. It's never going to go to infinity. It'll just keep going. Right? And if we look at what the total energy is, it's shown there. But I'll draw a line for it. Here's the total energy you guessed, 10. Now, what would happen if you guessed a bigger number? If you guess a bigger number, the kinetic energy is going to be bigger. So the curvature divided by the amplitude is going to be bigger. That is, the curvature is going to be bigger. It's going to be a sharper wave. So we check. Somebody guess a higher number. Mary Helen?
25.
25. Okay, so I'll get a new solution here. 25. Bingo. Right? And see the blue one, can you see it well? There's light coming in here, but there's a red curve and a blue curve here. And the blue one is a finer wave. Right? Now, I'm going to guess a number instead of Mary Helen's, and my number is going to be 40. What do you notice about 40 as compared to 10? Here's the first one, 10. Now I'm guessing 40. And notice the blue curve is going up and down more often, sharper. But you notice anything special? Look here. They match here and here and here and here and here, and this comes halfway between. Right? It's half the wavelength, but 4 times the energy. It has to do with the square root. 4 times as much energy, but 4 times as much energy means twice the curvature. Okay, it's just sort of an interesting thing. But anyhow, you can see that if we chose any number at all, it's going to work. It's just going to give a wave like this. Okay, so we solved it. Mary Helen, you guessed a good one. It's a new mark. Right? Congratulations. It's, in other words, the energy is not quantized. I can choose any energy I want and just get a different wavelength. Okay? So let's try a different one. Let's have a decay exponential. And let me make the picture bigger again. Maximum up. Say 60 again. And fill up the screen. Okay, so just and you little energy on. Get a new solution. Okay, so remember what we have. This is the potential energy, right? It becomes zero out here. It's a decaying exponential, right? When you get in here, the potential energy is quite high. Okay. Now we're going to guess the total energy and see whether Schrödinger will be allowed, whether it will go to infinity. Where are we going to have trouble? Remember, when you're in a region with negative kinetic energy, it's going to curve away from the baseline, so it will go toward infinity. And all this region to the left of here is negative kinetic energy, depending on what we choose for our energy. So let's just choose one like 10 again. So out here, this is the total energy. This is the potential energy. The total is bigger than the potential. It's a constant kinetic energy. And it's just like what we saw before in the sine wave. Okay? But here it's different. Because at this point, the potential energy is the same as the total energy, so the kinetic energy is zero. What's the curvature? Remember, the kinetic energy is the curvature divided by the value of the wave function. If the kinetic energy is zero, the curvature is zero. So at this point, above here, there's what's called an inflection point, when it changes from curving this way to curving this way. Remember, when it curves away from the baseline, it's got negative kinetic energy. So every place from the left of here, it's curving away from the baseline, and if it gets below, it's going to curve like this and go down. If it's above, it's going to curve and go up. But if you're just right, it'll go like this, right, and become zero. And you can have very large values of curvature divided by the wave divided by wave function, as long as the wave function itself is almost zero, right? Then the curvature is also almost zero, and it just becomes flat out here. So again, we can choose any value we want, right? No quantization. But if the particle is confined, so it's bounded on both sides, we're going to try that now. Now we're going to choose Hooke's law, which is like a spring. And we'll make the energy go up to 200 maybe. And fill the screen and show the total energy. Okay, now we need to guess again. And let Schrödinger turn the wheel and see what we get. So let me start you out with a guess. We don't have too much time. Let me start with 4. Now what do you see? It was just like before here. It has to be zero out here so it doesn't curve away. And it's curving away, okay? But when you get to this point where the potential and the kinetic energy are the same, you get this inflection point where it changes from curving up to curving down. Okay? And now it curves down like that. But here, when you pass this point, it starts curving up again, and zing, it goes off to infinity. No good. So, do you need more or less curvature in here? What do you want to happen on the right? You want it to come down on the right like this. So it's got to get further down here. So it has to curve more. So you need more energy. Sandy, you guess. For 4, we guess 4, right? That's not quite enough. So guess something. 8. Okay, so we'll try 8. 8. Bing. Now notice what that did. It went off to negative infinity. It's curving too much in here. What you wanted it to do is between these to come down like that. So 8 is significantly too high. Okay. 5. Try 5. We'll make that 8 into a 5. Yeah, there it is. It's a little better, but still it's curving too much. Another guess. What? 1. Oh, no, 1 is, no, you need more curvature than this one, right? So it gets down. It has to be bigger than 4, but it has to be less than 5. Bruce, you look like you're ready to guess.
I guess it sounds like 4.5.
4.5. Okay.
We'll try 4.5. 4.5.
It went a little, you notice it went a little further to the right, but not enough yet. It's still, 4.5 is still too big. Okay?
4.3.
4.3.
4.3. Better. Let me make it 4.2.
Ah, that was too hot. Too much energy. It curved down too much. It has to be less than 4.2.
So maybe 4.1. So I'll make this one 4.1.
Ah, that's up. So what do you know about the true energy that's going to work? There's going to be a true energy that works that does get right down here. But it's between 4.1 and 4.2. Now that's the beauty of a computer. Because you can have a computer do the same guessing you did, right?
The same way. So if I get a new solution here and make it 4.1, yes, 4.1. Okay, but then I'm going to press this thing that says solve and get something greater than that. And the green one, which you probably can't see, can you see there's a green line here? And it goes like this.
Yep.
So we did it, right? But notice it's quantized. They're only a very, very particular one. 4.14979614. Right? So if it's bounded on both sides, if you encounter this negative energy problem on both sides, then you don't have enough flexibility. It's going to go to infinity someplace. Right? But there's going to be some guess that will do this. Now, could there be any others? Well, you know, why don't we use this guessing game, this automatic guess to save a little time, and we'll try to get one that's bigger than this, and make the color black so you can see it. Okay, and notice this one worked too. It started here, went down, back up, and came to 0. It has to come to 0 here and there, so it's not good. The choice is that or infinity, which is not allowed. Okay, so we got 4. Now it's 12.44. Can you guess another one? What's the next one going to look like? The first we had one that just went up and down. Now up and down and up. Can there be another one? Wayne? Up, down, up, down. Right? So let's guess that. There, did it? See? Up, down, down. But the numbers, notice, were 4.1 something, 12 point something, 20 point something. They're evenly spaced at 8 units. And if we went to a really big number, like let's go up to 160. Right? And that's a small number. Okay, so there I've got 160. Here, notice that it said it solved, but it went off to negative infinity. That's because the computer doesn't have enough precision in the numbers to get exactly the right thing, but it's as close, it's the 10 significant figures, okay? So there are an infinite number of them, right? But they're always spaced at this same spacing. And the lowest one is the one that goes up and then down. So this is the lowest one. You can't have fewer than 0 times of crossing the baseline. And this one crossed it, 25 times or something like that. Okay, so it's quantized, yeah.
What is the significance of those? If you look at the tips of those things, you see how that creates a junction?
I couldn't hear for a lot.
You see the tips of those things at the top and the bottom of each one of those things?
The tips, like here?
Yeah, and you see that together that created curvature.
Yeah, good question. What does psi mean? We've used psi as a tool to find the energies that are allowed, but we don't know what it means, right? Obviously, the shape of those curves have nothing to do with what it means. Okay, we can play a lot of games with this that my students did, but let's go back to the PowerPoint. That was Erwin meets Goldilocks. Notice where the name came from? You guess too hot, too cold, but there's one that's just right. Yeah? So that's the way Schrödinger is quantized. Okay, now, we only wish that we could glean an inkling of what psi could mean. Okay, what does it mean? Well, Max Born in June 1926, so 6 months after it was originally formulated, he wrote a paper from which this comes. It says, if one wishes to translate this result into physical terms, that is to interpret it, only one interpretation is possible. Psi signifies probability of the position. So there are different positions the particle have. Psi tells you how likely it is to be there. But an interesting thing about this is the footnote. See the footnote up here? And if you look down below at what the footnote says, it says correction in proof. More careful consideration shows that the probability is proportional to the square of the size of psi. I think that's just fascinating. That Max Born, who gets the Nobel Prize for this, says psi is the probability when it can be positive or negative. You can't have a negative probability, right? So it was corrected in proof anyhow, and that's what it is. The square of psi is the probability. So let's go back to square these things that we were looking at. Okay, so now if we press this button here, we show the square of psi plotted down at the bottom. This is the square of the red curve. So it's most likely to be here, but the probability falls off. And notice, incidentally, that it can get beyond, remember this point here is where the potential and the kinetic energy, or the total energy and the potential energy are the same. Kinetic energy is 0. Anything to the right of here, all this probability is a region of negative kinetic energy. It actually happens. It's not just a possibility. Every atom you have, which has electrons bound in it, they're bound, meaning they have negative kinetic energy when they get too far. Every one has this property of electron spends time where it has negative kinetic energy. Okay? And now let's look at the other one here. Oops. I did that by mistake. And now we get to Martin's question. This is the square, so this is the probability. Now, think about this. This thing oscillating like that. Suppose I had a camera, or a movie camera, and I took a whole bunch of pictures. How many would have, what fraction of them, that is, what's the probability of it? How many of them have it in the middle compared to those having it at the end? Do you think it's more likely to be in the middle or at the end? How many think in the middle is the most likely place? How many think at the end is the most likely place? And why is it at the end? Because it's going so slowly there. In the middle, it's going fast, so you don't get many pictures that catch it in the middle. But at the end, it's going very slowly. So classically, the way this works, the thing is most likely at the ends, and then it's less likely in the middle, and then goes up. But quantum mechanically, this one it's most likely in the middle, and less at the ends. But when you get to a high quantum number, it becomes like the classical one, with the horns on the end. Okay, so this is where we were. So psi squared is probability. What did Einstein think of this? He wrote a letter to Max Born in December. So Schrödinger was January. Born's psi squared interpretation was June. This is December. This is what Einstein said to Born. But an inner voice tells me that this is not the real thing. The theory yields a great deal. It can calculate all these energies, right? But it brings us no nearer to the secret of the old one. Right? Jedenfalls bin ich überzeugt, dass der nicht würfelt. Anyway, I am convinced that he does not play dice. Okay? So this is the Solvay Conference on Electrons and Photons, October the next year. Right? And here's Einstein with the worthies in the middle of the front row. Right? And if we pull it up a little bit, you see here's Einstein. He's 48 years old. He's not so old, but he's older than a lot of people there. And he considers himself old because his great work was done in 1905, right? 22 years earlier. Right? But here is Max Born. He's only 4 years younger than Einstein, but he's of a new generation, really, this probability thing.
And back here is Schrödinger, who is still younger at 40. And these two young whippersnappers are Pauli, who was 27, and Heisenberg, who was 25. So the young people can get a different point of view than what Einstein had, who says he doesn't play dice. Right? Now, in 1927, this is Richard Feynman. Okay? Now, he got older as well. So when he was 64 in 1982, he wrote this: "We always have had a great deal of difficulty in understanding the worldview that quantum mechanics represents. At least I do, because I'm an old enough man that I haven't got to the point that this stuff is obvious to me." Okay, I still get nervous with it. You know how it always is. Every new idea, it takes a generation or two until it becomes obvious that there's no real problem. It has not yet become obvious to me that there's no real problem. I cannot define the real problem, therefore I suspect there's no real problem, but I'm not sure there's no real problem. Okay? So that's the next generation, right? And then you get another generation, and you come to a guy that was born the year before I was, and was 1 year ahead of me in college, Charles Jenks. And if you know of Charles Jenks, does anybody know of Charles Jenks? He's a landform architect and a critic of architecture and art. Right? So this is his garden, the garden of cosmic speculation at Dumfries in Scotland. And you see, it's just full of waves and all things that have to do with cosmic speculation. And the greenhouse is what's really interesting. This is the greenhouse, and notice up on top of the greenhouse, he's got Schrödinger's equation for the probability. Right here's del squared, the curvature of psi and v, and so on. It's on the top of his greenhouse. So this is becoming second nature to people in my generation, but even more so for the next generation. Here's my class 7 years ago, right? And here's Yoon Jun Lee, and she's the one that drew this cartoon of Goldilocks with energy that's too hot and too cold, and so on. And energy is quantized when a particle is surrounded by continuous regions of negative kinetic energy. So that's the idea. Okay? So, Jack, you can take off. He's waiting to drive to Ann Arbor. That's it, thanks.